Keshvanand Institute of Technology Management in Gramothan, Jaipur. Today, the topic of our discussion is traffic signal design. These are the contents of my presentation, which includes introduction to traffic signal, which is further subcategorized into definition of traffic signal, advantages and disadvantages of traffic signals, and different types of traffic signals available in the market. Terminologies which are related to traffic signal design, Webster method of traffic signal design with numerical, and IRC method of traffic signal design with numerical. We'll start the presentation with the introduction part. A traffic signal is a set of automatically operated colored light signal, typically red, amber and green in color, for controlling traffic at road junctions and pedestrians crossings. Basically, at a 4-legged or a 3-legged intersection where the PCU is greater than 3000 and we can't provide a rotary intersection or a channelized intersection there, we need to provide a traffic signal for orderly movement of traffic. This is a typical diagram of a traffic signal, in which red means stop, amber and yellow means caution, and green means go. There are many advantages of traffic signal. The traffic signal is used to control, regulate and guide the traffic, get free flow of traffic without unnecessary interruption and congestion. Traffic signals are very highly useful in reducing the road accidents by regulating the traffic, protect pedestrians from accident. They also provide a provision for pedestrian movement, provide general safety and efficiency to roadway, reduces right-angled crashes. They provide economy over manual control at the intersections. Like if we will use manual labor to control the traffic at the intersection, that will be a bit costly. So traffic signals are provided and they are economical over manual power. There are few disadvantages of traffic signals as well. Traffic signals are very highly useful at peak hour traffic, but if I'll talk about off-peak hour traffic, they are a bit less useful because they increases the total delay in the traffic. As the delay will increase, the fuel consumption will increase, which will finally result in air pollution. Traffic congestion also increases, induces road users to less appropriate routes. Disobedience of traffic signal is one of the major problems which may lead to high road accidents as well. Rear end collisions are also increased. Improper timings cause excessive delays. Like if I'll talk that give you an example, like majority of the traffic is flowing from north to south direction, and less traffic is flowing from east to west direction, and the green signal timing is high in east west and less in north south direction, so it will increase the delay, but it will increase the delay and it will create problem for the drivers. Failure of traffic signal is one more major problem as well. Electric failure may lead to confusion between the road users. There are 3 types of traffic signals available in the market. First one is manually operated signal. Manually operated signal are operated by a point near the traffic signal by a police constable. The signal phases may be varied depending upon the traffic demand at that time. The second and the cheapest type of traffic signals available in the market are fixed type signals. In this fixed type signals, a fixed phases of signals are being injected or introduced into the traffic signals, which is repeated again and again depending upon the study of that area. The third type of traffic signals are automatic or traffic actuated signals. These are the latest type of traffic signals and the costliest traffic signals available in the market. These traffic signals contains detectors which are installed at all traffic approaches. The green timings of the traffic signal varies depending upon the actual demand of traffic. These are the costliest traffic, but in India majorly fixed type automatic signals are used. The terminologies which are included in traffic signal design are: first, time cycle. The period of time required for the complete sequence of signal aspect at any one arm of an intersection from red to the onset of next red is known as cycle time. Phase: the part of signal cycle allocated any traffic movement or a combination of traffic movement. Amber period: interval between termination of green and exhibition of red signal is known as clearance amber. Amber signal is again flashed at the termination of red and exhibition of green signal. Intergreen period: this is the time from the end of green period of the phase losing right of way to the beginning of green period to the phase gaining right of way. All red period: this is a time when all the signals are red for pedestrian flow. This is a typical flow traffic signal diagram which should be drawn after designing of a traffic signal. There are two types of methods which are used in India for designing of traffic signal. First one is Webster method and second one is IRC method. We'll discuss both the methods along with their numericals. Firstly, we'll start with the Webster method. It has been found from studies that average delay and overall delay to the vehicles at a signalized intersection varies with the signal cycle length. If the signal cycle length is increased, the average delay per vehicle is reduced to a certain minimum value, and thereafter the delay also starts increasing. So when the delay is minimum, that cycle time is known as optimum cycle time, corresponding to the least overall delay. The optimum cycle time depends upon the geometric details of the intersection and the volume of traffic approaching the intersection from all approach roads during the design arc. Webster method is the best method for determining the optimum cycle time of the traffic signal. So again, I am reminding you, the optimum cycle time is that time at which the delay is minimum. Optimum cycle time is determined by the formula 1.5 L plus 5 upon 1 minus y, where L is known as total lost time per cycle in seconds. The formula is 2n plus r. Here n is number of phases and r is all red time. The total lost time, that is L, can be determined by another method also, which I will introduce in the IRC method. Here y is a constant which can be determined by y1 and y2. Y1, here 1 and 2 are representing road 1 and 2. Y1 can be determined by Q1 upon S1 and Y2 can be determined by Q2 upon S2. Here Q1 is the PCU of traffic on road 1 and Q2 is the PCU of traffic per hour on road 2. S1 is the saturation flow on road 1 and S2 is the saturation flow on road 2. Saturation flow is the maximum flow that can take place on that road per hour, allowing least or minimum headway. The green time on both the directions can be determined by this formula presented here. Y1 C0 minus L divided by capital Y, Y2 C0 minus L divided by capital Y. The saturation flow can be determined by this table, although there is a possibility that it can be mentioned in the question itself. If it is not mentioned, we can determine it by this table. For a 3 meter width, the PCU per hour is 1850. For 3.5, it's 1875. At 5.5, it's 2900 meters. At the road width greater than 5.5, it can be determined by 525 multiplied by multiplied by the width of the road. A numerical for Webster method. The average normal flow of a traffic on cross road 1 and 2 during design period are 500 and 300 PCU per hour. The saturation flow on these roads are estimated as 1200 and 1000 PCU per hour respectively. As I told you, the saturation flow there is a possibility that the saturation flow could be given in the question. Otherwise, we can determine it by this table. In this question, it is already given. The all red time required for pedestrian crossing is 12 seconds. Design the two-phase traffic signal by Webster method. We'll follow this design procedure for determining the Webster method. First, we'll start. The normal flow on road 1 and 2 are given as 500 and 300 PCU per hour. Saturation flow on road 1 and 2 are given by 1200 and 1000 PCU per hour. Number of phases which has to be determined is 2, as the traffic is flowing from this and this direction, so the two-phase traffic signal is required. Y1 is 500 divided by 1200, so it is coming out to be 0.42. Y2, it's Q2 upon S2, so Q2 traffic flowing is 300, saturation flow is 1000, so it is coming out to be 0.3. Total Y constant is coming out to be 0.72. Lost time will be 2, and its number of phases, that is 2. Total red time, all red time is 12 seconds, so total lost time is coming out to be 16 seconds. Optimum cycle time as per Webster method, as I told you earlier, also is denoted by C0, and the formula is 1.5 L plus 5 upon 1 minus Y. We have already determined the total lost time, that is 16 seconds, and capital value of Y constant is 0.72. The optimum cycle time is coming out to be 104 seconds. Now we will calculate the green signal time on road 1 which can be calculated by y1 upon capital Y C naught minus L. Y1 is coming out to be, we have already find out y1 is 0.42, capital Y is 0.72. So y1 0.42 upon 0.72, C naught is 104. Total delay is 16. It is coming out to be 51 seconds. Similarly, for second road, green time signal is coming out to be 37 seconds. Now we will have to determine the total signal length. So 51 seconds is green signal time for road 1. 37 seconds is green signal time for road 2. All red time for pedestrian is 12 seconds. We need to provide a amber time for clearance of 2 seconds on both the phases, phase 1 and phase 2. We have added 2 seconds of amber time, so it is coming out to be 104 seconds, which is a total optimum cycle time. We can draw the diagram here as well. When there is green signal at phase 1, there will be red signal at phase 2. After green signal, there will be a caution signal, that is amber signal of 2 seconds. Then there will be red signal of overall 39 seconds. In some countries, amber signal is again phased after red signal, but in India, after red signal, directly green signal comes. So we can provide 2 seconds of red amber signal. There is a possibility of amber signal here as well, or we can include it in red signal timings as well. Similarly, here the red time is of 51 seconds, after that red amber, then green signal time, after that amber time of 2 seconds. So this is the phase diagram of traffic signal, two-way traffic signal by Webster method. Hope this is clear to all of you. Now we will move towards IRC method of traffic signal design. IRC method of traffic signal design is almost same as Webster's approach, but a few minor variations in accordance with the guidelines of IRC are taken. IRC suggests a walking speed of 1.2 meter per second for pedestrians in designing of traffic signal, with the initial walk time of 7 seconds. Like for crossing a 6 meter long width road, 7 seconds of initial walk time plus 1.2 meter per second of speed of the pedestrian is considered. So 5 seconds will be required for crossing the road and 7 times of initial walk time. So total 12 seconds will be considered for the pedestrian to cross the road. The cycle time is calculated assuming an amber time of 2 seconds each. We have considered it in Webster method as well, amber time of 2 seconds. The minimum green time required for clearing the vehicles approaching from each road is determined assuming the first vehicle needs 6 seconds and all the subsequent ones need 2 seconds each. For example, the traffic is traveling from north to south direction. The vehicle standing in the first row will need to accelerate the traffic on green time. So it will need slightly more time than the proceeding vehicles to cross the road. So it is assumed that the first vehicle will need 6 seconds to cross the road and the proceeding vehicles can cross the road in 2 seconds each. The optimum signal time, which is calculated by IRC method, is then checked by Webster formula. If both are coming out to be almost equal, then it is accepted. The lost time is calculated from the amber time into green time and initial delay time of 4 seconds for the first vehicle of each leg. I'll explain it with the help of a numerical. We'll take the numerical in IRC method. At a right angle intersection of two roads, road A has 4 lanes and a total width of 12 meters and road B has 2 lanes with a total width of 6.6 meters. The volume of traffic approaching the intersection during design are 1800 PCU per hour on the two approach road A and 300 and 200 PCU per hour on the two approach road of road B. Design the signal typings as per IRC guidelines. Now we'll move towards the solution. We'll write what is given. Width of roadway A is 12 meters, which is a 4-lane road, 2 lane on both the sides. Width of road B is 6.6 meters, 2-lane road, 1 lane on each side. Approach volume on road A is 1800 PCU. Approach volume on road B is 300 and 200 PCU. We will design the traffic signals by the highest PCU. Like for road A, we'll design it for 1000 PCU per hour, and for road B, we'll design it for 300 PCU per hour. I have explained earlier as well, the pedestrian walkway speed is taken as 1.2 meter per second as per IRC guidelines. As I told you, it's a 4-lane road, 2 lane on each side. Design traffic on road A is 500 PCU per hour per lane. Design traffic on road B will be 300 PCU per hour per lane. Step 1, pedestrian crossing time. As I told you earlier as well, as I explained earlier as well, the initial walk time of 7 seconds has been explained by IRC, and 1.2 meter per second is the walking speed. So for road A, that is of 12 meters, 7 meters is the initial walk time plus 12 meters, that is the width of the road, and 1.2 meter per second is the speed. So it is coming out to be 10 seconds. 10 seconds plus 7 seconds, that is 17 seconds for road A. The pedestrian crossing time will be 17 seconds for road A. Similarly, for road B, it is coming out to be 12.5 seconds. Now we'll move towards step 2, minimum green time for traffic. Here, the pedestrian time is 12 seconds for road A. So minimum green time for road B will be 17 seconds. When there is a red signal on road A, there will be green signal on road B. So minimum time for red signal on road A will be 17 seconds. So the minimum green time on road B will be 17 seconds. If the minimum time of road B is 17 seconds, we can calculate the minimum green time on road A as per the traffic calculations. Like for 17 seconds on road B, 300 PCU per hour traffic is flowing. So for 500 PCU per hour traffic, how much time will be required? We can apply interpolation here. So for 17 into 500 upon 300, 28 seconds of green time will be, minimum green time will be required for road A. Now we'll move towards step 3, that is revised green time for traffic signal. Obviously, we'll have to add amber time and intergreen time of 2 seconds on both the faces. We'll have added 2 seconds of amber and 2 seconds of intergreen time on both the faces. So the optimum cycle time, a total cycle time, is coming out to be 53 seconds, which includes both red, amber and green time. Now we'll check the clearing of vehicles during green phase. How much time will it take to clear the vehicles? On road A, there are 500 PCU per hour per lane. Optimum cycle time is of 53 seconds. So 9.5 PCU per cycle can take place there. As I explained earlier as well, as per IRC guidelines, the vehicles in the frontmost lane, in the first lane, will have to start their vehicles and accelerate. So it will take 6 seconds for them to cross the traffic signal. So it is for first PCU plus 9.4 minus 1. First vehicle have been passed, so that is reduced. 8.4 are left into 2. There are 2 lanes, so that is multiplied by 2 here. So it is coming out to be 22.8 seconds. Sorry, it's not for 2 lane, it is 2 seconds for the vehicles after the first lane. So it is coming out to be 22.8 seconds. We are providing 28 seconds for road A. It is coming out to be 22.8 seconds, so it's okay. For road B, it is coming out to be 5.7 PCU per cycle. 6 seconds for first vehicle. First vehicle is subtracted from this PCU, 4.7 into 2 seconds for the proceeding vehicles. It is coming out to be 15.4 seconds, which is, we are providing 17 seconds for road B. So it is less than 17 seconds, hence it is acceptable. Now we will check as per the Webster method. We have calculated the lost time per cycle by the formula 2n plus r. We can calculate it by another method as well. As we can see here, 2 seconds is amber and 2 seconds is intergreen time. That are also delays in which the vehicle can't cross the traffic signal. So 4 seconds is introduced here. 2 seconds are required for the proceeding vehicles to cross the traffic signal, and 6 seconds are required for the first lane vehicle to cross the traffic signal. So 4-second delay is happening here as well for the first lane vehicle. So we have applied a delay of 4 seconds here. It's a 2-phase signal, so it is multiplied by 2. A total delay is coming out to be 16 seconds. We have to calculate saturation flow on road A and B. We can calculate it by using this table, which I explained in Webster method. this table. So by using this table on road A, the saturation flow is coming out to be 3150 PCU per hour, and on road B it is coming out to be 1865 PCU per hour. Y1 and Y2 are calculated. Y1 is Q1 upon S1. Q1 is the PCU per hour at peak hour traffic, that is 1000, and Q2 is 300 peak hour on road 2 or road B. We can say road B, it is 300. It is saturation flow 3150. On road B, saturation flow is 1865. Y1 and Y2 are coming out to be 0.32 and 0.16. Total Y constant is coming out to be 0.48. Optimum cycle time can be calculated again by formula 1.5 L plus 5 upon 1 minus Y. L total delay is 16 seconds. Y is 0.48. It is coming out to be 56 seconds. We have calculated by IRC method total cycle time of 53 seconds, and by Webster method is coming out to be 56 seconds. So it is approximately, there is not a very huge difference. So 53 seconds is acceptable. We can draw the signal phase diagram like we did in Webster method here as well. By this, we can calculate the traffic signal designed by IRC method. Thank you for your time. For any further queries, you can mail me to nishant.sachdeva@skit.ac.in or nishantsachdeva15@gmail.com. Thank you.